A very good evening, friends, and in this video we are going to discuss about the differentiation using formulas. In the previous videos we discussed about the first principle or the ab initio method, and using the first principle we learned that how we can find the differentiation of a given function directly at any point, that is the general expression, or how to find the differentiation at a particular point. And before that we have also discussed that when a function is said to be differentiable, that is the idea of the limit, and then the limit has to exist. So for that the left hand limit and the right hand limit both should exist and their value should be same, then only the function can be differentiable. Now every time when you are given a function to differentiate, then you cannot just go for the first principle or the ab initio method. We will use the formulas. Now in the previous videos also we had just a little bit of understanding of the formula, that how these formulas have come up. Now again I am extending from the very same. Now here you know that suppose we have a function fx is e to the power x, then if you differentiate this, then f dash x will become fx e to the power x. So the function is e to the power x, and then its differentiation is also e to the power x. Now people say that you can just by heart this formula, but those who are keen to understand the concepts of the mathematics, they should know that how this formula have come up. So again for that we will be using first principle method. So f dash x is limit h tends to 0 f x plus h minus fx over h. Now limit h tends to 0, this x plus h, since the function is fx is e to the power x, and when we have to find fx plus h, so replace x by x plus h. So this function fx plus h will become e to the power x plus h minus e to the power x over h. Now limit h tends to 0, we can take e to the power x common, then we will be left with e to the power h minus 1 over h. Now see, here we have the limit h tends to 0 and e to the power x is independent of h, so you can just take it as a constant and take it outside, because when h is tending to 0, then e to the power x would remain unaffected by the changes in h. So we will write e to the power x limit h tends to 0 e to the power h minus 1 over h. And those who have studied the limit properly, they must be knowing that this is the value 1. So it is e to the power x into 1. Therefore f dash x is nothing but e to the power x, because this is the formula for the limit, that the limit h tends to 0 e to the power x minus 1 over h is 1. So e to the power x into 1 will become this function. This is how this formula have come up. Now I'll take few more examples to explain you my point of view, but before that I would like to clear the screen. Now I take another function that fx is tan x, and its differentiation, that is f dash x equals sec square x. So again we'll go by the formula that f dash x is limit h tends to 0 fx plus h minus fx over h. Now here you can see that since fx is tan x, then fx plus h will just be tan x plus h. So here this becomes limit h tends to 0 tan x plus h minus tan x over h. So this is the tan x plus h minus x. Now you know that the tan x is sin x over cos x. So tan x is sine x over cos x. And since this is just the limit and we have some values of the limit also, so instead we'd like to convert this tan x plus h as sine x over cos x. So this becomes limit h tends to 0 sine x plus h over cos x plus h minus sine x over cos x and whole divided by h. So here I write limit h tends to 0. If you take the LCM, then you get just sine x plus h into cos x. So this will become sine x plus h cos x minus sine x cos x plus h over this LCM will be cos x into cos x plus h, so I put that also down. So this will become h cos x cos x plus h. Now here this is just look at this term properly. So this is sine x plus h cos x minus sine x cos x plus h. It means this is sine a cos b minus sine a cos b minus cos a sine b. So this is the formula for sine a minus b. So now what this will become, I need to clear the screen first. So okay, so now I just draw a line here. So this is, you will have limit h tends to 0. This is sine a minus b. So sine x plus h minus x over h cos x plus h. So this x and x cancels. Okay, so now I have to put the value. Those who have done limit properly, they know that we are getting a term sine h over h. So this is my sine h over h, and then this term I can write separately, cos x plus h. Now we will put limit h tends to 0 in both these cases. Limit h tends to 0. This will become 1 and this will become, because x plus h where h is 0, so it will become cos x. So cos x into cos x is cos square x. 1 over cos square x is sec square x. So now there is, you see that the differentiation of the function is tan x. Differentiation of the function f x tan x is f dash x is sec square x. So we are also getting sec square x, means this is the formula. Now I'll do one more for the inverse trigonometric functions, and then the rest you can manage on your own. So every formula what we use in differentiation has been derived by using the first principle method. So now I'm writing just some of the formulas directly instead of deriving them, so you can understand that this is the fx on the left side, and on the right hand side we have their derivative. So if function is x to the power n, its derivative is nx to the power n minus 1. If function is e to the power x, derivative is also e to the power x. If function is e to the power x, its derivative is e to the power x log a. If function is log x to the base e, then its derivative is just 1 over x. If function is sine x, its derivative is cos x. If function is cos x, its derivative is minus sine x. If function is tan x, its derivative is sec square x. This you have seen. This formula and this formula I have derived. Sin x also, if I remember correctly. And other formulas like this differentiation of cot x is minus cosec square x. It can be derived the very same way, the way you have derived the value of tan x. Now for sec x, it is sec x tan x, and for cosec x, it is minus cosec x cot x. In the trigonometric ratios, you see that all the c terms, c for cos, cot and cosec, they have their derivatives negative, like minus sin x, minus cosec square x, and the minus cosec x cot x, and the rest are all positive. Now there is one more property. What is the dy by dx of a constant? Dy by dx is 0 if y equal to fk, a constant function. Now how? That you can see that if you write the formula, f dash x is limit h tends to 0, fx plus h minus fx over h. This x plus h means x is incremented by a value h. Now if you have a constant function, that you know that the constants do not change, only the variables change. So the constant function means even if you are incrementing in x by h, there will be no corresponding change in the value of function. So this one will remain fk only, and this one is also fk over h, and so this is 0 because fk minus fk over h is 0. So differentiation of a constant value is 0. So this is the formulas, and now we will be discussing some basic concepts, how to apply these differentiations rules in the implicit functions or the explicit functions or in the algebraical relations. So in the next video we'll discuss that in much in detail.